The PSF department is studying planet and star formation, and we are actually combining observations at large-scale facilities, both from the ground and from space. So recently, the James Webb Space Telescope, with numerical simulations and experimental work in our laboratory. We want to understand how stars form, what the rate of star formation is in our and other galaxies, but we also want to understand how planets form, the micron-sized particles which are located in so-called protoplanetary disks around young stars. These tiny particles have to come together, they collide and grow, and at some point they form planets, and they also form the atmospheres of planets. We're also hunting for young planetary systems by adaptive optics assisted observations where we correct the atmosphere and get very sharp images. But we also use the JWST and other space instrumentation to get very sharp pictures, but also spectra of young stars. And we recently found water in the inner regions of this. And in our lab, we tried to find out what kind of conditions we have and what kind of chemical reactions occur under the early Earth conditions, but also in the interstellar medium and in protoplanetary disks, and how that is actually connected to the origins of life. We're called dusty objects, like the protoplanetary disks, and molecules like water shine in the infrared. But part of our atmosphere is actually opaque to infrared wavelengths. So we need to go to space to get sensitive observations. And we have a long tradition to do that. We are part of the Infrared Space Observatory of Herschel, and now we are part of JWST, the largest space-based telescope we ever launched.
James Webb hat 4 Instrumente an Bord und eines davon ist das Mittelinfrarotinstrument MIRI. Das ist die Kamera und der Spektrometer für die längsten Wellenlängen. Das heißt, man kann da die kühlsten Objekte sehen, man kann auch am tiefsten in die Staubwolken hineinschauen und man kann auch am weitesten der Zeit zurückschauen. Und das ist im Prinzip ein sehr spannendes Instrument, weil es uns eben erlauben wird, die entferntesten Objekte zu sehen, die kurz nach dem Urknall entstanden sind. Das ist eine der großen Fragen von James Webb. Wie sind die frühesten Galaxien in unserem Universum entstanden? Wie sind die ersten Sterne entstanden? Wie unterscheiden die sich von unseren heutigen Sternen? Und da hat James Webb jetzt auch schon wirklich interessante Entdeckungen gemacht. Und im Infraroten kann man eben auch, vor allem mit MIRI, ganz interessante Moleküle sehen, wie zum Beispiel Wasser auf fremden Planeten, auf extrasolaren Planeten, die um ferne Sterne kreisen.
We joined the JWST project in the year 2000, and now 20 years later we can actually get the scientific harvest. One of the great results was the discovery of water in the zone where we expect terrestrial planets to exist. On top of that, we found an amazing soup of molecules in low mass disks, starting from simple hydrocarbons to even benzene. So we now see this world we never had seen before, and this is a fascinating time to be part of the JWST mission. So in order to kickstart life on rocky planets, we need organic molecules. So we have to form these organic molecules either under early Earth conditions or in interstellar space and protoplanetary disks. And indeed, we see a soup of organic molecules in comets. We see that in asteroids. We also found a lot of molecules in disks. But we not always understand how these molecules are formed because they're sitting in very low temperatures under extreme radiation conditions. We want to find out how that happens, and therefore we have established a lab, and Jiao He is the head of this lab here in Heidelberg.
My research mostly focuses on the formation of prebiotic molecules in space, particularly in a dense molecular cloud condition where star and planetary system are formed. One of the most important hypotheses about regarding the origins of life is that the prebiotic molecules, the building blocks of life, they come from the space, they are delivered to the early Earth in the form of meteorites and comets. Where are the origin of comets and meteorites? They can eventually be traced back to a molecular cloud in space. What we do in the laboratory is that we try to simulate the physical and the chemical conditions in the molecular cloud and see what kind of chemistry can happen to produce those organic molecules, particularly prebiotic molecules. We started the laboratory back in 2020 from zero, from an empty space, and we put all of the small pieces together to make a big machine. We built a large vacuum system, and we have a cryostat to cool down our sample. We spend a lot of time to do the instrumentation. We do a lot of testing, make sure everything is working fine. In the molecular cloud, where the solar system was originated, the dust particles are covered by an ice mantle made of water and carbon monoxide. The ice mantle consists of more or less two layers. The inner layer is dominated by water, but the outer layer is dominated by carbon monoxide. It is in the outer carbon monoxide dominated layer most of the complex organic molecules and prebiotic molecules are formed. My experiments find that the carbon monoxide ice has a phase transition from amorphous phase to polycrystalline phase at that very low temperature. And during the phase transition, the impurities or other reactants, atoms and small molecules, can segregate and they're pushed together, and reaction can happen during the phase transition. This may be one of the most important mechanisms to make prebiotic molecules in dense molecular cloud. So far, our research has been focused on relatively small molecules like water, hydrogen, and methanol, etc. And we haven't really looked at the formation of large prebiotic molecules such as nuclear bases or even something bigger like nucleosides or even nucleotides. And we have built a large machine particularly for this kind of topic. We have a new ultra-high vacuum system, a very high sensitivity, a very high resolution mass spectrometer called Orbitrap to identify prebiotic molecules. And our hope is that by using this kind of high sensitivity, high accuracy machine, we can identify large molecules in the ice mantle. It is already confirmed that we can produce molecules such as nuclear bases and amino acids, sugar molecules in the ice mantle if we do irradiation to the ice mixture. So one of our next research topic is to look at the formation of nucleosides in the ice mantle. I hope in the next 1 or 2 years we are able to find out whether nucleosides can be produced in the ice mantle in dense molecular cloud.
But we are already thinking about the next mission, so we are part of Rowan. This is a US mission, and we provided all the mechanisms for the chronographic instrument to image planets. So the goal is actually in the future to get images of Earth-like planets and to measure their atmospheres. This is a long-term endeavor, and we are now preparing for the necessary steps. But the really fun part of the story is that every day we can still discover something because we have new eyes like JWST or the ELT. We can combine that with large-scale numerical simulations, and we can do experiments. And the other ingredient is, of course, it's a great group of people. Students and postdocs from all over the world are coming to our department, and we are joining forces to produce great science. And diversity is not a challenge, it's just wonderful to have.